Hey everybody, this is Mr. Beckstrom, and today we're going to be taking a look at section 4.4. This is graphing functions. So really what we're doing is we're taking everything that we've learned, even stuff from pre-calculus, and using it to graph some of these functions kind of by hand. We're also going to be using the calculator, but we'll have enough information from going through all of this junk here to get a really good idea of what this graph is going to look like. I'm not going to kind of go over it all detailed because that's just a whole lot of reading, but what I will do is put up an example, and then we'll use that example to kind of make sure that we hit all of those points there. Alright, so let's take a look at this function here. It's x cubed minus 6x squared minus 135x. If you want to go through and see if you can locate all of these steps with that, do that now. That's really the best. And then when you're ready, we'll go through the solution. Just go ahead and unpause it and we'll go through the solution. All right. So for this one, I just want to kind of hit step by step. So the first thing, says identify the domain or interval of interest. On what interval should the function be graphed? It may be the domain of the function or some subset of the function. So first of all, this is a polynomial, so it's going to be continuous and differentiable for all values of x. So negative infinity to positive infinity. But really, what we're trying to do is we're trying to graph the intercepts and the local mins and the local maxes. So once we find those here, that'll give us a good window in order to graph that in, especially where the highest y value, the lowest y value, and we can do that by plugging in the values. So I'm going to kind of come back to this a little bit here, or really that's actually part of 9 as well, choosing an appropriate graphing window to make a graph. But there's no, they didn't give us an interval in order to graph here, and we're definitely, like I said, continuous and differentiable everywhere, so no real limit. All right, next thing it does is says exploit symmetry. Take advantage of symmetry, for example, if the function is even, or if the function is odd, or if it's neither. Well, I can tell you right now that this one is neither even nor odd, because it's a polynomial with both odd degrees and even degrees, and I just know from experience that means that it's neither even nor odd. If it were even, then it would be reflective across the y-axis there. And if it were odd, it would be reflective across the origin. So we can kind of use that to help us graph it later. But neither, so this is not really going to help us here. All right, it says first find the first and second derivatives. All right, so I'm going to give myself some space here. And let's do the first derivative. So the first derivative is f prime of x, just using the power rule, is 3x squared minus 12x minus 135. I'm running out of room there. And then the second derivative down here, so I just write it like this, is just the derivative of the first derivative. So that's just going to be equal to 6x minus 12. 6x minus 12. All right. They are needed to determine extreme values, concavity, inflection points, and intervals of increase and decrease. Computing derivatives, particularly second derivatives, may not be practical, so some functions may need to be graphed without complete derivative information. All right, so we found those. Find the critical points and possible inflection points. All right, and critical points is when the derivative, the first derivative, is either equal to 0 or undefined, and the inflection points are where the second derivative is equal to 0. And inflection points are where the graph is going to go from concave down to concave up, or from concave up to concave down. So let me give myself a little bit more space here. Oops. I didn't mean to move that. I meant to move the whole thing here. All right, so what we're going to do here is for this function here, let's go ahead and factor out that 3 and then I'm going to get an x squared minus 4x minus 45. And if we set that equal to 0 and factor it, we're going to get x, I think this was minus 9, and x plus 5 is equal to 0. Therefore, our critical values of this function are negative 4 and positive 9. So, since these are critical values, these are the values where we could have local maxes and local mins. So let's find that out here. We can do that with a little interval here. All right, so we're going to have a negative 4 over here, and we're going to have a 9 over here. And this time, I just put in values here to see if they come out positive or negative. If I put in 0, I'm going to get a negative number. So more than likely, this is going to be a positive over here and a positive over there. But let's just use the calculator to figure that out here, so we don't make any mistakes. So if I go to y equals, and I put in 3x squared minus 12x minus 12x minus 135, and I go to make sure it's on ask, and then I go to my table there, delete those out, and we'll check, so something less than negative 4, so we'll check negative 5, up. How did that become 0? Hold on, let me check something. Oh, I see what I did here. I put a negative 4, should have been a negative 5 there, so hopefully you caught my mistake. All right, let me do that again. So that's a negative 5 right there. All right, sometimes you go too fast here. So this should also be a negative 5. So we need something less than negative 5. So let's go back here. Let's put negative 6. And we get a positive. And then, like I said, if we put in a 0, we get a negative. And put in something greater than 9, so we'll put 10 in there. 10 in there, and we get a positive. So it goes positive, negative, positive. That means at negative 5, it's going up and then down. So we're going to have a local max. And at 9, it's going down and then up, so we'll have a local min there. All right, now let's take a look at the second derivative test here. If we put those values, see, this is actually two ways to do the same thing. So we already have the local max and the local min, but if we were going to put the negative 5 in there, we'd have negative 30 minus 12, negative 30. Let me make sure. Looks like a good 12. Negative 30 minus 12, which is definitely a negative number. Therefore, it is concave down at x equals negative 5, which we already knew that because we kind of did the increasing, decreasing deal. And if we put a 9 in there, that would be 9 times 6, which is, oh my gosh, 54, and 54 minus 12 is positive as well. So that means it's concave up at 9, which we already knew that from this test. So you really don't need to do both of those to figure out whether it is a local min or a local max. You just need to do one of those. All right, but now we want to find the points of inflection. So I am going to go ahead and factor that, x minus 2. So we have 1 point of inflection at, why does it disappear on me? If I put it back in, it's just going to show back up there. Oh, there it goes, see? All right, so that means x equals 2 is a point of inflection. So that means at 2, it's going from concave down to concave up. Concave up. All right. And let's pull this back over here. So we did that. We found the intervals on which the function is increasing, decreasing, concave up, and concave down. All right. Identify the extreme values and inflection points. So what we're going to do here is find these points here. So the inflection point, let's go to our calculator here and put the original function in, which it is not. So we'll do x cubed minus 6x squared minus 135x, 135x, and let's start finding out what all these values are. So our point of inflection, and if we just go back over here and we plug in the x value, 2, so we have a point of inflection at 2, negative 286. So this is really at 2, negative 286. And let's find where this local max is. So I'm just going to put in that negative 5 there. So negative 5. That's at 400. So this point here is at negative 5, 400. And then 9. Just plug in that 9 there. I get negative 972. So our local min is at 9, negative 972. So, yeah, I think that's it for that one. Let me just double check here. Oh, so the critical points, both the x and y coordinates of the maxima and minima, and inflection points are needed. All right, so locate all the vertical and horizontal asymptotes and determine the end behavior. So for this function here, grab another thing. There's not going to be any vertical asymptotes because there's nowhere that this is undefined. And as far as horizontal asymptotes, we're not going to have any horizontal asymptotes either. We really only take a look at those when we're dealing with quotients, right? A function on the top and a function on the bottom. So we don't need to worry about that one for this one. Hopefully I'll pick a function that we can do that with for the next example. Locate the intercepts. Well, we can do that from here. So this is, we can pull out an x, and we're going to get x squared minus 6x minus 135. And that is going to factor to x, I think, minus 15 and x plus 9. Which means that we're going to have x-intercepts at 0, 15, and negative 9. So x is equal to 0, 15, and negative 9 here. Now what about the y-intercepts? Well, when we let x equal 0, then y is also equal to 0, right? Because that zeroes out. So it's going to correspond to this x-intercept here at 0. All right. Now we need to choose the appropriate graph. So that's where we use these points to really do that. So our y max should be a little above 400. Our y min should be a little below 972. For our, let me see, that fits in there nicely. And then for our x values, we need to make sure that we go back past or to the left of negative 9 and to the right of 15. So I think I may have already set this up here. So I went from negative 10 to 20. I changed that to 2. And then I went from negative 1,000 on my y's to include that negative 972 all the way up to positive 500. And you change your scales a little bit. Roughly, your scale should be about 10% of your values, but it doesn't matter that much. It's just if your scale is too small, you'll get a whole bunch of little lines in the graph. All right, and then I graph it, and this is what it looks like. This is what it looks like. So this point up here, that's going to be negative 5, 400. This is 0, 0. At 2, negative 286. This is where it's going from concave down, and then right here we have an inflection point, and it turns to concave up. And then here is our local minimum at negative 972. All right, I hope this helped. I'm going to go ahead and look at one more example. Okay, so for this next function here, I have f of x is equal to 3x over x squared minus 1. So go ahead, see which steps you can do with it. And really, I'm just going to kind of go over the steps that we didn't do for the last function because it didn't really make sense for that one. All right, so pause the video, see how far you can get, and then we'll go over the solution here. Okay, so the first thing is identify the domain or interval of interest. All right, so if we factor this here, let's go ahead and do that now. So this is equal to 3x all over x plus 1 and x minus 1, right? I'm having trouble writing here. Okay, x plus 1 and x minus 1. All right, so neither of these are going to factor out, so it looks like we're going to have vertical asymptotes at -1 and +1. But other than those two vertical asymptotes, the function is defined for every other x value other than those two, and they didn't give us a specific interval. So exploit symmetry. This is actually an odd function. Let's verify that real quick here. So if I replace x with negative x with negative x, I don't know if you remember this from pre-calculus, but let me know if you have trouble with this. What I do here is I replace all of the x's with a negative x all over negative x squared minus 1. And then when I simplify this, I'm going to end up getting a -3 over x squared minus 1. So this function here is just the negative of this function up here. And that means that the function is reflective across the origin. So for every value x, y, there's going to be a value -x, -y. So if you have 2, 3, then you should also have the value -2, -3. So we can use that if we were just trying to graph this by hand here. All right, find the first and second derivatives. I'll let you go ahead and do that using the quotient rule. So it says find the critical points and possible inflection points. That's using those derivatives there, and then increasing, decreasing. So go ahead, make sure that you can do that. You're going to go ahead and use the quotient rule there, and you may need to use the quotient rule again after that to find the inflection points. Or, in order, because you'll definitely need that for the inflection points. And then the vertical and horizontal asymptotes, that's one that I wanted to do on this one. So we're going to have vertical asymptotes at -1 and +1. And we're going to have a horizontal asymptote at 0. And the way we can do that is, if you remember when the exponent on the bottom, which is 2, is larger than the exponent on the top, which is 1, then we have a horizontal asymptote at y is equal to 0. That's the x-axis there. And let's see here. Find the intercepts. Find the intercepts. So by doing that, we know that if we let x equal 0, then y is going to be equal to 0. So 0, 0. That's right. That's right. And we also, to find the, that's to find the y-intercept. To find the x-intercepts, we set the y equal to 0. And really, that's just the top there, so that's just the same one. And choose the appropriate graphing window, so you can go ahead and do that. So let's take a look at this function in here and see what it looks like. And this is what it looks like. So this is our only intercept here at 0, 0. Notice that everything kind of on the upper right is the same as the lower left, and everything on the upper left is the same as the lower right. That's because the function is odd. Notice we have that horizontal asymptote as the x-axis here, y equals 0, and then we also have two vertical asymptotes, one at positive 1 and one at negative 1. All right, well, that's it for today. If you do have trouble getting that first and second derivative, let me know in the forums, and I'll go through doing that. But hopefully we're getting pretty good with the quotient rule by now. All right, y'all. Thank you, and have a great rest of your week.